Okay, so starting with position versus time graphs, the slope of a position versus time graph would just be the rise over run, change in position over time, which is going to give you velocity or your speed. Makes sense because that's meters over seconds, which gives you velocity meters per second. So you can tell which object is moving faster by the graph that has the biggest slope, which would then be the steepest. If that graph goes up, that means it's moving in the positive or the forward direction. If it is decreasing graph, then that's moving in the negative or the backwards position. If the object is moving at a constant velocity, that means the slope would be constant, which means the graph would be straight. If the object is changing speed, then the graph would be curved or not straight. What that looks like if it is slowing down, so slowing down would be getting flatter, something like this or this, and if it is getting faster, then the graph would be getting steeper, something like this or this. Area under the graph would be multiplying the two. When you find area, you're multiplying x and y. Position times time would be meters times seconds, which doesn't give me anything. That means nothing. And occasionally you'll be asked for instantaneous velocity. That would just be velocity at that point, which if it's constant, you can just find the velocity of the section. For a velocity versus time graph, these are the super important graphs because you can do a lot more with them. So the slope of this would be change of velocity over time, which is going to give me acceleration. Remember, slope is just rise over run, meters per second over another second gives me meters per second squared, which is acceleration. If the graph is going up, that means I have a positive slope or a positive acceleration. If it's going down, I have a negative slope or a negative acceleration. To tell if it's moving or forward or backwards, you just look at the sign of the velocity. Anywhere in here, that's a negative velocity that is moving backwards. And anywhere in here, that is a positive velocity moving forwards. Whether it's speeding up or slowing down is whether it's speeding up would be going away from zero, or slowing down would be going towards velocity of zero. If it is moving with a constant acceleration, then your velocity of time graph should be straight lines. That is most of the case. Area here is super, super important. When you multiply velocity times time, that's meters per second times seconds. That cancels out, leaves me meters, which is your displacement, or your delta x. Points to note, if your velocity and your acceleration are opposite signs, so if I have positive velocity and negative acceleration, or negative velocity and positive acceleration, both of these cases, because these are in opposite directions, that means your object is slowing down, will slow down. If the velocity and acceleration are the same signs, so positive velocity, positive acceleration, negative velocity, negative acceleration, that means that your object will speed up, get faster. Projectile motion. So normally we would make our chart x and y. X and y are completely separate. The only thing that they would share is the time, because the time it takes to fall down is also the time that it's going sideways. Which component has an acceleration? Well, the only thing acting on it is gravity. Gravity points down, so it has an acceleration in the y component. So acceleration for y is negative 10, or g. And what do we know about horizontal motion? Well, we do have an acceleration in the y component. For the y component, for horizontal, there's no x acceleration. So because there's no x acceleration, that means it must be going at a constant velocity, right? It's not accelerating, it's not speeding up or slowing down. Doesn't mean it's not moving, it's just not accelerating, so it's constant velocity. And because it's at a constant velocity, the equation we should always use for x will be v equals delta x over t. That is for projectile motion. That does not mean anytime anything is ever moving sideways, then you have to use this. It's possible you have a car on a road going in the x direction and accelerating. This is for projectile motion. The x component will always be constant velocity, so I can use that equation. And your vertical or your y velocity would be 0 at the top, where it's changing directions, changing between going up and down between a positive and negative velocity. So it would be at the top or the highest point. Most often for projectiles, we have the horizontal projectile, something like this. So for our xy chart, let's say this was v, that would be an x velocity. And then because I shot it horizontally, I did not shoot it up or down, so my initial velocity in the y component would just be 0. Because I only shot it sideways. I didn't shoot it up or down with any initial vertical velocity. And then the component x or y that determines the time in the air. Well, if I shoot it faster this way, that doesn't make it spend any more time in the air. But if I were to shoot it down with some initial velocity down, or I were to increase the height or change anything in y, that would change the time. So the time is determined by the y variable. The position, velocity, and acceleration graphs for a low friction basically means ignore friction, cart placed on the ramp show. So for the first part of the ramp, it is going to start with an initial velocity of 0, so I'm going to start right here. And I made this the negative direction just because it was going down. I will show you what it would look like if you made that the positive because I didn't specify. So let's say this was negative. I start from 0 and I know that I'm going to accelerate as I go down because this is an incline, right? It's not exactly gravity. It wouldn't have an acceleration of 10. That would be if it was just straight down. But I have some component of the gravity that's accelerating down. So because I have an acceleration, that would be a negative acceleration down, this is going to speed up for the first part. So increasing speed and a constant acceleration. That brings us to this part. Then, once I've accelerated and I've sped up, once I get here, now I don't have acceleration anymore. It's not going to be speeding up. It's not gaining speed in here because there's no component of the gravity. It's not an incline. But there's also nothing to slow it down, right? It says low friction, so ignore friction. So I don't have an acceleration slowing it down. I just don't have anything speeding it up anymore. So that would be jumping up to 0 acceleration. And because this is not accelerating, again, I'm not going back to velocity 0. I didn't slow down. There's nothing to slow me down. It's just not accelerating anymore. So then I would cruise at a constant velocity that it was at. And then my position graph. So my position, I'm going to have it going down because I said this is the negative direction. I'm going to start slow and get faster. So that would look like getting steeper. And then the last part would just be straight. So I'm going to start flat, get steeper, and then I'm just going to continue at a straight line. So that last jump would be at the constant velocity, and this is showing you getting steeper. Now, if you decided, let me do this in red pen, if I decided that this was the positive velocity, or positive direction, that's fine. Your graphs would be, I have some positive acceleration, and then it jumps to 0. I start at 0, I get faster, and then I continue at that speed. I start going up, I get faster, it gets steeper, and then I continue at a straight line. It'd be the same, it would just be flipped up, as long as they were all matching. If you had this one and this one, that doesn't make sense. You have all this or all of that, that's fine. At what time does the object pass through its initial position again? So here, we're looking at a velocity versus time graph. Position has to do with how far you've moved, so basically we're looking at area. So I have this negative area, and then I have this negative area. So all this time I've been moving backwards. So I'm not going to pass through my original position anytime here, because I just moved backwards the whole time. Now from 4 to 5, I started to move forward, but that's not enough to make up for this back here. So I'm not back where I started, so let's look. 6 looks like maybe you're not quite sure, and then if you were to continue, we're checking just each of these, right? After 7, that would be way too far. So 5 is too little, 8 and 7 would be way too far, so 6 is the correct answer. For what time interval does it move the greatest distance? So I'm going to look at each of these 1-second intervals at their areas. And the single section that has the greatest amount of area was from 6 to 7, because it has the greatest area right there. We are ranking the magnitude of the average acceleration during the 3 sections. So again, acceleration would be the slope, but for magnitude, we don't worry about sign, so don't care about sign. We're just looking at, is it bigger or more or less, not positive or negative. So I have 3 different slopes. I have this one, and this one. Now these 2 are clearly equal to each other because they go down 4 and 2 versus up 4 and 2. So both have an acceleration of 2. It's just this one is negative 2. And then here I'm going up 12 in 3 seconds. This has an acceleration of 4. So then the greatest acceleration, if we're just looking at magnitude, the greatest acceleration is the 4, which was from 4 to 7 seconds. And then these 2 are opposite signs but equal in magnitude. So 4 to 7 and then the other 2 are equal, that's D. 4 to 7 has the greatest acceleration and then these 2 are equal to each other. We've got a cart with negligible, meaning I can ignore it. Friction, it's given some initial velocity up the ramp and the cart rises a distance, turns around, travels back towards the motion sensor. Which set of signs describes the cart's displacement, velocity, and acceleration at the moment when it's at the highest point on the ramp? And it tells me that away from the sensor, so in that direction, that is our positive direction. So So I'm starting with some initial velocity, I've got some v naught going this way, and I know as I go up, it's going to be slowing down, and then I'll stop and I'll turn around and come back this way. So the fact that it started going up this way and it's slowing down tells me that my acceleration is down. Also, gravity, right? Down the ramp is the way it's going to accelerate. And then that means my acceleration is going back towards the motion sensor, so that would be a negative acceleration. So automatically, we're looking at A. But the reason why your velocity is 0 is because it asks specifically at the top. Between having a positive velocity and a negative velocity going down, you have to stop for a second, right? 0 between positive and negative. Also, you have to stop to turn around. So that instant at the top, you would have a velocity of 0 as it changes directions. And then your displacement is positive because you're at positive displacement in the positive direction away from where you started. Very similar, I start with some initial velocity that is not 0. So I made this direction right here the positive direction. It doesn't matter if yours would just be flipped the other way if you didn't, because I didn't specify, whereas here I did. But I made this direction positive, so I'm going to start with some initial velocity that way that is not 0. So I start with a positive initial velocity, and then again, you have an acceleration. This is v naught. You've got an acceleration against you in the opposite direction, because it would accelerate down the ramp. So that's going to slow you down until you're 0 at the top, and then you turn around, and now you're going to get faster and faster in that negative direction. Constant acceleration in the negative direction. Right, a car moves at a constant velocity, so that would be flat. Slows to a stop, so that would be going to v equals 0. And then without pause moves in the opposite direction, so that means that velocity changes signs. With the same acceleration. So the only one that changed signs at all is actually A. What this would be doing is speeding up, constant velocity, slow back down to rest. This one is constant velocity, slows down, and then speeds back up in the positive direction. So neither of these changed signs. This one, constant velocity, said it would be flat, slow down to rest, it did go to 0, and then now I'm speeding up in the negative direction with that same acceleration, the same slope. Right, our position versus time graph. So moving forward means it's going up. Constant velocity means that it's going to be with a straight or a constant slope, so a straight line. So when it's going up straight is graph 3. Backwards, it means it's going down. Again, constant velocity is a straight line or a constant slope, so that would be graph 5. Moving forward and speeding up. So moving forward is again going upwards, but now I'm getting steeper. So I'm getting faster, so going forward and getting steeper would be graph 1, to see how it becomes more and more vertical as I go. And now I'm moving backwards, so going down and speeding up, so again, getting steeper. So these are both going backwards, but only this one is getting steeper, so graph 2. Moving forward, going up, but slowing down is getting flatter. So the one that these two are, these two are both getting flatter, but this one is actually going up, so that would be moving forward, graph 4. And then lastly, this one is moving backwards, but again, getting flatter would be getting slower, so 6. Now the velocity versus time graph that goes with each of these. So 3, we said, was forward. That's a positive velocity, and it's constant. So I want positive, constant velocity. The only two that are constant are these two, and the only one that's positive of these is v. Backwards at a constant velocity, so that's just a negative velocity. Again, constant, so that would be b. Moving forward and speeding up, so I've got a positive velocity, and it's getting away from 0, because I'm getting faster. So positive velocity and getting away from 0, that would be f. Moving backwards and speeding up, so this is now negative, going away from 0. So negative away from 0 is A. Both of these are slowing down, which means they're going to v equals 0. Going forward is a positive velocity. The only one that's positive and going to 0 is c. And then moving backwards, negative velocity going towards 0 is d. If you're like, wait, but that's negative. Actually, that's a negative slope, which means a negative acceleration, but the actual velocity values are positive numbers on this y-axis. All right, the driver of a car going at a velocity v makes an emergency stop, slams on the car's brakes, and skids to a stop. How far would this car have skidded if they'd been traveling at twice that velocity? So definitely going twice as fast you're going to take a longer distance to stop, so you can cross off B. Now, all of these are longer distances. We need to know the actual factor, so I need to look at the equation. So I'm going to say my initial velocity, some V. I know it goes to a stop, so my final V is 0. How far is delta x? Now, it didn't say anything about acceleration, but either way, if I'm slamming on the car's brakes, no matter what speed I'm going at, that should be the same acceleration. I should have said like with the same acceleration, but let's call it A. Now I'm not going to use T because it is not going to be the same amount of time to slam on the brakes going twice the velocity. That would take more time, but A should be the same. So then now pick an equation that relates the two velocities A and delta x. That's the third equation. This would be 0. V naught, we're calling V. 2A delta x, subtract over. Divide 2a over. So what I have is that delta x is v squared over 2a. And it's minus just because it's stopping, so acceleration is going to be the opposite sign of the initial velocity. Now, if I were to double the velocity, which is the whole point of getting this, is to see if doubling the velocity, what would that do to my delta x? Well, this is getting squared right here. So if I were to put a 2 in front of the v, really that 2 would get squared as well. So that would be a factor of 4 times the displacement. So 4 times as far A. If that had been a square root, and I had anything x, right, or what is it, v right here, and I were to double that, then that would be root 2 bigger. If it was just v with a bunch of other stuff, not squared or square rooted, if I doubled v, then that would be 2 times the displacement. But that's not what's happening. It was v squared, so doubling v would be 4 times as far. 10, the greatest distance. So for a velocity versus time graph, distance is just your area under the curve. So I'm going to break these up. So the greatest area of each of these is just A to B. Don't spend time actually calculate. I don't know how you would calculate this curve, but don't spend time actually calculating when you could just be like, oh, that's clearly bigger. Right, a ball is thrown with a speed of 10 at some angle, so I'm throwing it up at some angle like this. Sketch the velocity and acceleration graphs for both horizontal and vertical components. So I'm going to start with acceleration because I know for something flying through the air, the only acceleration that I'm going to have is gravity. Gravity is pulling down, so that would be a y acceleration, right? Gravity pulls down. And it's a negative constant acceleration. It's negative 10 at every single point. Now, in the x direction, you don't have a sideways acceleration. The only force acting on it is gravity, which pulls down. There's nothing making it go faster or slower or sideways, so I should have 0 acceleration for x. Now, what no acceleration means is not that it's not moving. That doesn't mean I can't have a velocity. It just means I'm not accelerating. I'm not speeding up or slowing down. I'm staying at the same velocity, constant velocity. So that's easy, constant velocity. And then lastly, my y velocity is not constant, right? It has an acceleration. It starts going up. It would be 0 at the top, and then it gets faster on the way down. So I'm going to start with some positive velocity at the beginning, and then on its way up, that y velocity, again, we're just looking at y, not the x. I know the x, I know it's moving to the side the whole time. That's why x is constant. But my y velocity starts upwards and slows down. It's 0 here, and then it gets faster in the negative direction. So slows to 0, and then gets faster in the negative direction. Given the velocity versus time graph, I want to know at what time does the object pass through its initial position again. So we're looking at velocity versus time. Back at the same position is when your displacement equals 0. So that means my positive displacement must cancel out with my negative. I have my option between 1 and 2, so let's look. I'm actually moving backwards all through here, so there's no way by the time I get to 2 that I've made up for that, so I can cross off this. Now between 3 and 4, so let's look. So somewhere from here to here, that between these 2 seconds, yeah, that's reasonable. And then let's look between 5 and 6. So at 5, I am way past my initial position, so it can't be between 5 and 6. And then 6 and 7 again, like way past my initial position, so B is the only one that makes sense. You don't need to spend time actually doing the math if they're obviously not the others, right? Like, be careful with your multiple choice, don't waste time you don't have. All right, ranking magnitude of acceleration in the 4 different sections. So the easiest one is that this one right here is flat. This is an acceleration of 0. If we're looking at magnitude, it doesn't matter if it's positive or negative. 0 would be the slowest or the least acceleration you can have. So from, 2 to 5? 2 to 5 is for sure my last acceleration. So cross off these. And then now we're checking, this is 2 in 1 second, that's acceleration -2. This goes up 3 in 1 second, that's acceleration of 3. 1 in 1, that's acceleration of 1. So the 3, the 1 to 2, is definitely my fastest. 1 to 2, and then this one, and then this one, and then 0 would be the least acceleration. 5 kilogram box starts from rest, v equals 0, accelerates at this rate. Speed after it's moved 2 meters, that's your delta x. Looking for speed after, so then now you're just plugging in v squared equals v naught squared plus 2a delta x. If you're like, where did she use this equation? Why didn't she use the first two? Well, I didn't ask for time, and I'm not given time, so why would I plug into one with time? When I could just plug in, relate the two velocities a and delta x. Right, so I'm going to plug in, looking for v, this is 0 squared, 2, 1.4 times 2, so that's v squared equals 5.6. So then the last step to get v by itself is to take the square root, and that gives you, actually I don't know, 2.36, 2 point something meters per second. Right, velocity versus time graph shown. In which interval does it travel the farthest distance? So we can get distance or how far it's moved from a velocity graph by the area under the curve. So in each of these, the greatest area would be this chunk right here, 20 to 30 seconds, C. Velocity graph determining if each of these is true or false. So slowing down from 4 to 6. Actually, my speed is going from 0 to 2 to 4 to 6 to 8. It happens to be negative, but I am definitely getting faster. So that is false. You are getting faster. I'm at rest from 0 to 4. Definitely not true. You have a velocity of 4 there. At rest would be a velocity of 0, so that's false. Magnitude of the acceleration from 3 to 6 is greater than the acceleration from 8 to 10. So let's look. Here, you can do the whole thing, or you can just do the part. I just saw that it went down 4 in 1 second, so that's an acceleration of -4. You also can say that's 12 in 3 seconds, still -4. And then here, I did 8 in 2 seconds, so that's an acceleration of +4. I'm just looking at magnitude, so these are the same magnitude. That one is not greater, so false. It changes directions at 4 seconds. I absolutely agree. Before I had a positive velocity, now I have a negative velocity. So think about that as like going up and then going down. 0 is where it switched. So that one is true. It ends behind its initial position. Let's look at the areas. I definitely travel a lot farther backwards than I did forward, so I'm ending behind where I started. True. Slowing down from 8 to 10, that is a velocity of -8 to -6 to -4 to -2, going towards a velocity of 0. That is slowing down, agreed. And the object passes its initial position somewhere between 6 and 7. So this right here, definitely not here, right? Too little. Here, still too little. Here, yeah, probably somewhere in here that looks like it might be over, and then definitely over in here, so 6 to 7. Yes, that one works. If you actually do the math, this one is 14. At 6, you've only gotten 8, but then at 7, you've got another 8, so that would be at 16. So somewhere between 8 and 16, you pass through the 14. You've like undone the 14 you forward you did. This one had the typo. Remember, you're supposed to fix that to C and then D. We have 2 correct answers. This is a position graph because that's x measured in meters. 10, C and D have the same velocity. Actually, no, they have the same position right here. The velocity would be the slope, and they do not have the same slope, so that's not true. At 10, C is passing D. Yes, that is true. Because beforehand, C was behind, and then after 10 seconds, now C is in front, so that means it must have passed them. C is moving with a constant velocity, and D is moving a constant velocity that's faster. They are both moving with constant velocities because they are straight, but C is the steeper line, so C is the faster velocity, so that is not true. And D starts with head start. Yes, at the very, very beginning, D has an initial position ahead of C, so that one was true, it has a head start. And lastly, our velocity versus time graph. So we just said that they both are constant velocities, they're both positive, but they're not the same. C, we said, was a steeper line, so it's a higher velocity. So this would be like C, and this would be D. Both constant and positive, it's just C is a little bit higher because it is a little bit faster.